Right. So, uh, can you see the screen? Is the screen visible?
Yes, so the screen is visible.
All right. So, the standard error, it is defined here. This is the formula. That's the standard error of beta 2 hat. And this is the standard error of beta 1 hat. To see the relationship between the two, if you take the square root of this thing, you would get this equation. And if you take the square root of this thing, you'll get this equation. So they are one and the same, except for the fact that the one is the square root of the other. So if you take the square root of variance, beta 2 hat, it equals standard error beta 2 hat. So if we want to discuss regarding standard error, or if there is something that applies to standard error also applies to variance. So if we make our discussion with reference to variance or standard error, it doesn't matter at all because one is the square root of the other. So I'll be referring to variance sometimes and standard error at other times, but you should understand the context of the discussion by knowing the fact that these two are just the square root and square of each other. So we discussed yesterday that these are all the x's, and then this is sigma. This is a new thing for us. That's for population, and we can never get sigma. There's no way to get sigma and sigma squared. So what we need is its estimator from the sample, which is nothing but sigma hat and sigma hat squared, and we can get sigma hat squared like this from the residuals, right? So if we know the residuals, all of these, that means we know sigma squared or sigma hat squared, right? Using this formula. So I said that I'll be explaining yn minus 2 in the denominator later. So I'll be doing it today. Another thing is RSS. I'll explain this also today. First, let us understand the formulas better. So the first uh, result that we get from this formula is that if you keep this constant, if you don't change the numerator, and if you increase the denominator, this thing will fall. Falling this thing, falling variance beta 2 hat means more precision, right? That's what is written here. Given the value of sigma squared, the larger the variation in x values, that means higher the denominator, the variance of beta 2 hat, and hence greater the precision, smaller the variance of beta 2 hat, this thing is small, and hence greater the precision with which beta 2 can be estimated. Look, there's no hat here, right? Because we want to estimate beta 2 using the estimator beta 2 hat. Beta 2 hat is the estimator of beta 2, right? So the precision in knowing beta 2, the precision with which we can say something about beta 2, or knowing the value of beta 2 with some precision, depends upon standard error of beta 2 hat, right? So that's the connect between the sample and population, and it comes through standard error, right? This is the concept that links these two things. So I'll say more about this. Point number two, given the variation in x values, the larger the value of sigma squared, the larger the variance of beta 2, right? So here, uh, it is said that for a given variation in x values, for example, if this is given, the denominator is given. So this time we are not changing the denominator. We are keeping it fixed. So this is given and fixed, right? So for a given denominator or for a given variation in x values, the larger the value of sigma squared, larger the numerator, larger the variance of beta 2, higher is the variance beta 2 hat, right? So what does it mean? It means that if there is a given x variance, so x values are spread through some distance, and then if we raise sigma squared. Now how can you raise sigma squared? See the formula. How can you raise this? You can raise this by raising the numerator, right? So in effect, we are saying that if we raise summation ui hat squared, and then you can think of a plot, this plot, and this plot. So it has a low summation ui hat squared, and this one has a high summation ui hat squared, right? Do you agree with me? Do you agree?
Sir, I didn't understand what was the
Okay.
main point here.
All right. All right. You
Sir,
you
can you please try to go a little slow for this? Cause now there's a bit of lag in the
all right.
the device
So
you use.
let me ask all of you, how many of you are feeling the lag so much that it is inevitable for me to go a little bit slowly? Please raise your hands. 7 raised hands. If you want to raise more hands, you can keep them raised, because I want to count how many of you are might be facing the problem. So I have to look into the problem. If the problem is a big problem, all right. So I got 7 hands. Please, you can lower the hands now. Okay. So that means there is little problem that has to be solved, because there are 7 people. It's not specific to Satvik, but it is happening with others also. So I'll try to be slow. There might be a lag. I mean, I agree with it. There will be a lag, but the question is that whether the lag is so much that I have to be slow and I have to take care of it while teaching.
So
Uh,
the thing happens, your voice is not lagging. So the screen when you share na,
hmm.
uh, when your cursor is moving perfectly fine, but when you make everything, the thing shows up a bit late.
Okay.
Like the lines you draw, the things you write, the cursor goes, but the things come a bit late.
All
Like
right.
the words show up a bit late.
All right. So when I'm drawing something, and when I'm making a lot of marks using my pen, then that appears with a bit of lag.
So
So,
everything you write, everything appears with a bit of lag.
okay, whatever,
Just
whenever I'm using my pen, it is
yes, sir.
appearing on the on your screen, but with some lag, 2 3 seconds lag, 5 seconds
Yes,
lag.
sir. 5 seconds lags. Yes, sir.
Okay.
Like when you wrote, na, did you agree? So
Hmm.
it came after we said answers. Like it came afterwards.
Okay. So I got it. So I'll try to keep pace with what I'm writing and what I'm speaking. Let me try. If you feel better, it's okay. If you don't, do let me know later also. All right.
Okay, sir.
So, uh, did anyone understand what I just said here? So let me repeat because it's some time which has passed. So I'm saying that there is something called summation ui hat squared. It's a very familiar quantity to you. I've talked a lot about it in the past also. So that is nothing but sum of residuals squared, summation ui hat squared, this thing. Now I am saying that this can be high, this can be low. It's one number. Remember 2 3 things about this number. It's a one number, point number one. I'm talking about summation ui hat squared. It is one number. Point number two, it is representative of the entire regression. So for a given regression, you have one unique sigma ui hat squared, and it's a number, right? Two things should be clear. Then point number three is that this is summation ui hat squared is big if points are far from line, right? 3 points to note. Now I have drawn point number three on a graph. You can see when points were close to the line in the first graph A, we had low summation ui hat squared, and when the points are far away from the line in graph B, we have high summation ui hat squared. So when do we have a low summation ui hat squared? You can think of this type of graph A. When you have a high sigma ui hat squared, you can think of graph B in your mind, right? So I'm saying that let's go back to what we were discussing. We were saying that for a given denominator, summation is xi squared, if the numerator has a larger value or if it rises, so sigma squared rises, then variance would rise, variance beta 2 would rise. So in this explanation, I'm trying to explain how sigma squared can rise. Because sigma squared is calculated using summation ui hat squared, for sigma squared to rise, summation ui hat square has to rise. How can you have a big summation ui hat squared? If the line is far from points, or if the points are far from line, that is graph B, right? So in this case, variance beta 2 will be high. That means precision will be low. Precision would be low. Standard error would be high, right? Now, practically, you can think, intuitively, you can think without looking at the graph, at anything, just you can think that if sigma squared is high, that means there is more variability in the data points. Of course, you cannot estimate variance beta 2 hat or standard error beta 2 hat with great precision, right? You cannot calculate standard error beta 2 hat with great precision. Just intuitively, you can understand that standard error precision should be low when points are scattered like this. This is the line and these are the points very far away. So you can think, okay, this line is going from here. Now in the population, the line might have gone from here, right? So that if you are fitting some uh, interval onto the beta 2 hat that you have measured from the sample, that interval should be large, right? So you don't have that much certainty with which you are saying you are connecting beta 2 hat with beta 2. That certainty is not there, right? So this is the intuitive understanding of point number two. Now, point number three, as sample size increases, the precision also increases. So how can that be so here? So let us talk about sample size. Sample size n, right? So when you are increasing the sample size, okay. Before coming to that, before going to that this point, let me clarify, or not clarify, but give you some understanding of what is desirable and what is not desirable from the point of view of regression. What do you actually want? When will
So,
you be happy?
sir, you are trying to say that the larger our sample would be, the more accurate it will be with respect to our population, because
Exactly,
the deviation will decrease.
exactly.
But
You
sir, this is very obvious. Like when we study law of large numbers, so it talks about this only, that the greater the number, the more accurate it would be. This is what we've studied in statistics when we studied law of large numbers, right? So it's just the illustration of that.
larger sample means more precision.
So sir, it's the same law, right?
No, it's not the same law. I mean, it is pointing to the same law, but I will be explaining it from a different perspective.
All right, sir.
So I am taking for granted that you know this, right? You know this, that larger sample means more precision. And I'll start from here and try to put whatever I'm explaining in this slide into some context so that you can match it with your past knowledge that larger sample means more precision, right? So I'll come to it. Just let me say one more thing here before coming to this point. Uh, what do you want? When will you be happy as a researcher? What is desirable? These type of questions, right? You want sigma squared to be low. You want variance beta 2 hat vis-a-vis standard error beta 2 hat to be what? Low or high? Low. That is good, right? And you want summation xi squared to be high. You will be happy if these things are true. One, two, and three. Three things. Then it makes you happy, right? Why you are happy if sigma squared is low? Because if sigma squared is low, variance standard error beta 2 is low, and then you have more precision and you are happy. Why are you happy when standard error beta 2 hat is low? Because if standard error is low, that's what you wanted. You want to be more precise, and standard low standard error beta 2 hat means you are more precise and you are happy. Why sigma xi squared should be low, should be high? Because if this is high, then again standard error would be low. And when standard error is low, again you are happy because you are more precise. So you want to be more precise. For precision, you want your standard error or variance of the estimator to be low. For that to be low, you want your sigma squared to be low, or and your summation xi squared to be high. So did you get here what I am saying? These 3 points. Did you get it? Am I audible?
Yes, yes, you're audible and we understood also.
Great. So this is what we want. That is what is desirable. These three boxes in blue, right? Now let us come back to the point to this point number 3, sample size. All right. So uh, if sample size n is high, then summation xi squared will also be high. Do you agree?
Yes, sir. Sorry. You asked us what?
I asked if sample size n is high, then sigma xi squared will also be high.
Yes, sir.
Can anyone explain how?
Because the summation of the sigma will increase, and the mean would may not increase by that much amount. So capital X minus mean would be a bigger number. That's why xi would be higher.
All right. Okay, so let me explain it like this. So let me find a place somewhere here. So suppose you have some x's, capital X's, and you have these numbers, and then you want to calculate small x, which is x minus x bar. Then whatever x bar is and whatever this each x is, you will get some numbers here. These may be positive, maybe negative, maybe positive, maybe negative, but you want x squared, so they will all be positive, all positive, and then you add them to get summation x squared, right? Let me put a I everywhere. I, 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 and I, right? So there are these many numbers here. Suppose you extend it by adding few more numbers. Whatever numbers they are, doesn't matter. Big numbers, small numbers, positive numbers, negative numbers. But suppose you added some numbers, 1, 2, 3. Then what happens to this number? It will always rise. This will always rise. Sigma xi squared will always rise because whatever numbers these are bigger than the mean, smaller than the mean, positive numbers, negative numbers, whatever they are. These will be whatever positive, negative, but their squares will always be positive. And when you add three more numbers which are greater than zero to this number, summation xi squared, this will always rise.
Sir, so my explanation was correct, no?
Yes, yes, your explanation was correct. I just explained it to everyone who is listening so that you can get an understanding. So now this, what I was saying, what I wanted to explain. Yeah, here, here. Right. So if sample size increases because the denominator increases in the standard error formula of both beta 1 and beta 2, therefore precision rises, right? Because if sample size increases, summation xi squared rises. When that is what we want. You can see what we want. There are three things. One of them is this thing, right? That's what we want. So if this rises, then standard error would fall, and when standard error falls, we are happy because we are more precise, right? So it says that as sample size increases, precision also increases with the reasoning that I just gave you. So these are three important points. These are just the explanations of the formulas. So if you understood all of these, we can move ahead. Do you want me to explain any one of these again?
Understood.
What about others?
Understood, sir.
Great. So let's talk about, so I'll come back. So I have a lot of proofs to do. I have a lot of proofs to do, right? So in those proofs, I'll be explaining a few things which I have been mentioning that, okay, I'll explain it later. I'll explain it later. I'll talk about it. I'll talk about it. Because those need some mathematical proofs, right? So I have some proofs to do, which I will do. So at that time, this will also be included there, right? So it talks about covariance, and we will talk about it in those proofs. Then this last thing that I want to do before I go to proofs is Gauss-Markov theorem. And let me do it very quickly today, if possible. It's
Excuse
a,
me, sir.
yeah,
So could you please just explain the n minus 2 thing again? I understood those 3 points, just the n minus 2 thing. Like, why did we subtract it 2?
okay, n minus 2. Which one? I mean, are you talking about this n
Since,
minus 2?
yes, sir, yes, sir.
So I did not explain this. I did not explain this yet, right? I will explain it later.
Okay, sir.
Yeah, I did not say anything about this n minus 2. I'll talk about it later, right? So there are some things piling up which I need to explain. So I'll do it in one go because they are very related and they are related with proofs, right? Some maths. So we have to do that to understand those things. So Gauss-Markov theorem, this is a very important theorem in in regression. We have already seen what are the assumptions of the classical linear regression model. We have talked about the assumptions, right? And remember, I want to stress on this fact again. These are all about population, right? And we had a discussion on this. Now, given the assumptions, the least square estimates possess some ideal properties, right? And these are statistical properties that is being referred to here. And these are contained in this theorem called Gauss-Markov theorem. And what are these? It says that any estimator, for example, beta 2 hat, any estimator, any OLS estimator, ordinary least squares estimator, for example, beta 2 hat, is said to be best, linear, and unbiased, or blue estimator, B for best, L for linear, U for unbiased, E for estimator, best linear unbiased estimator of beta 2, which is population parameter, if the following hold, right? So we are saying that, of course, given the assumptions, that means given that they are satisfied, any OLS estimator like beta 2 hat, like beta 2 hat, you can call it blue if these hold. What holds? Number one, if it is linear. Number two, if it is unbiased. Number three, if it is efficient, right? So let me write these. Three things are important. You can call it blue properties, which are statistical properties. Number one, linear. Number two, if the estimator is unbiased. Number three, if the estimator is efficient. Three things are required for the Gauss-Markov theorem, which says that any estimator is blue if these hold, right? So when the assumptions are satisfied, the OLS estimators like beta 1 hat, beta 2 hat, these estimators, they possess some wonderful statistical properties, and those are blue properties, and properties say that the estimator is linear, the estimator is unbiased, and the estimator is efficient. So we have to understand the meaning of all these three. Number one, linearity. So you know what is linearity, right?
Yes, so that means there should be only they should be linear in parameter, and there should be only one parameter, and they should not have multiple parameters, or the parameters should not have degrees over it.
Right. So we can put that in another word. We can say that beta 2 hat is a linear function of a random variable, such as the dependent variable y in the regression model, right? Mathematically, this is another way of saying the same thing, where I can write where f is a linear function, right? This f is a linear function. So beta 2 depends upon some random variable in a linear way, in a linear fashion, right? So it's another way of saying the same thing. That means beta 2 is linear in variable, is linear in parameters, and it's a linear function of the data that we have. And out of our data, we have y and x, and out of these two, y is a random variable, x is not, right? That's what we assumed. X is fixed in repeated sampling. So that's why I wrote a y here, right? So there's a random variable, and whatever beta 2 hat would be, it depends upon that random variable, and that too in a linear way. It is linearly related to y. Point number two says that it is unbiased, right? Unbiasedness means it's a property of the estimators like beta 2 hat. It means that the expected value of the estimator, for example, beta 2 hat, is equal to the true population parameter beta 2, right? It means that the estimator beta 2 hat is unbiased. So the result is beta 2 hat is an unbiased estimator of beta 2, right? If this equation holds true, right? Unbiasedness means this equation in the box, expected value of beta 2 hat is equal to beta 2, right? So
So,
what is,
but how will we measure it? Like, how will we measure beta 2?
no, we will never measure beta 2.
So how do we know that it's unbiased or not if we are not able to compare both of them?
Yeah, so we will not be able to get the value of beta 2. We will be talking about probabilities only, but from the assumptions that we make about population, right? We made some assumptions about population, right? So we know our population up to a level because we have made some assumptions about the population. So if those assumptions are held are true, that means we have an idea of our population. Given the assumptions, we can think of, we can prove it mathematically that given the assumptions, this thing on the left, expected value of beta 2 hat, is actually equal to beta 2. So we will prove it using assumptions.
So, sir, we'll be learning this when we will come to proofs.
Yeah, we will be learning this proof also.
Sir, as you told that beta 2 hat is the estimator of beta 2.
Yeah.
So the expected value of beta 2 hat is the value equal to beta 2.
Yes.
Sir, can you explain that a little bit? Like,
Okay. Okay. I'm saying that expected value of beta 2 hat is equal to beta 2. It means that on an average, beta 2 hat is equal to beta 2 on an average. Of course, we have beta 2s, sampling distribution of beta 2s. Sampling distribution of beta 2 means that we have a lot of values of beta 2 because we have collected, if we collect all possible samples of size n, then we will have one beta 2 for each sample, one beta 2 hat for each sample, and we have thousands and thousands of values, or let us say millions of values of beta 2 hat for each sample, one for each sample, right? Then this sampling distribution, which is nothing but a probability density distribution function, or you can say probability distribution, it has a mean.
yes, so the mean is the sampling distribution of beta 2 hat.
Yeah. So the mean of the sampling distribution of all these million numbers, beta 2 hat, is nothing but expected value of beta 2 hat, right? So its mean is equal to beta 2, right? The mean of the sampling distribution of the beta 2 hats that we get when we collect all possible samples of size n from the same population and take and use OLS to calculate beta 2 hat for each sample. And then if we take the mean of that, of all those values of beta 2 hat, what we get is the true population parameter. This
Okay,
is
sir.
this is the property of the OLS estimator. You can take beta 2 hat or beta 1 hat for both of them. This is true. And this is called, what I want to explain right now is, what is the meaning of unbiasedness? Unbiasedness means that on an average, the expectation of beta 2 hat is equal to beta 2, right? This is called unbiasedness. Now, the last thing, efficiency. What is efficiency? It is again a property of the estimators, and efficiency means minimum variance property.
So, so actually, we have our next class. So, can you please take it up in the next class?
Okay, so okay, the time is up.
Yes, sir. It's 55, and then we'll get late for class.
All right. All right, so we can stop here and we will continue next time.
Thank you, sir. Also, sir, could you please upload yesterday's and today's recording?
Okay, I'll do it.
Okay,
Thank you,
thank you
sir.
very much, sir.
Okay, thank you. Please give me the attendance, all of you. Anyone
Yes, sir.
send me the attendance.
Two students are absent. I'll send you the names.
All right, all right. All right then, thank you. Have a nice day.
Thank you, sir.